He's so mad at you.
I'm a starter.
Gossip.
Yeah, you had that.
Want to know a really disturbing fact I found out about our handbook? It does not prohibit battery powered chainsaws.
I think you have a good team.
Internal combustion engines aren't allowed, but there's like a chainsaw. Unless the
Get a 24 out of 60.
There shouldn't be a lot of
2%.
threes or twos or.
Chainsaws are not banned from the laws.
It depends on how you look at the blade, because the chain I would have counted as a blade.
School.
It's not, that is a blade, it's a bunch of little blades, so it's not.
You could feel that one of these.
Yeah.
Like,
You can say collectively, that's like taking all your knives and putting them together. You
Right.
didn't say that.
There's gonna be a new clause in the rules about battery operated chainsaws.
I'm still waiting for one of you to show up with a mini horse and say it's my official sport animal.
I think I can afford a mini horse.
I'm kind of waiting for
I mean, mini horse, Great Dane, they're essentially the same thing.
Looks like we're gonna be getting the sound.
You guys need one, I'll show you guys what.
You guys should all be very familiar with sound because there's a lot of freaking noise in this room. I just use that in every class. You have a ton of compression waves.
This is 14. I went.
So if you're looking at this, first off, someone tell me. Let's look at the difference between like a sound wave and a light wave. So if you're watching Star Wars and you want to know what the space battle would actually be like, put it on mute.
That's right.
And actually the big fiery explosions, get rid of those.
I love Star Wars. I love Star Wars. He was here for this.
But if,
He just wasn't here for.
why do you think light propagates through space but sound doesn't?
Because it's an electromagnetic wave.
More direct.
Yeah, light is an electromagnetic wave, pretty well self-contained inside the photon.
Exactly what I was.
What about a sound wave?
Mechanical wave.
Mechanical wave. So how does sound propagate through the air?
It like pushes the molecule.
Yeah, so it's a compression wave.
Brandon.
So
Brandon.
you ever turn on your stereo and you see your speaker doing this? That's actually a mimic of this. That's the sound wave. So it comes out, the molecules in the air, they get compressed, they get moved around, and that ends up getting to your ear, which acts a lot like a piezoelectric crystal. You guys are
So we just all got our anatomy exams back.
really bad.
Well, no, but the B exam version was like screwed up. Empathy, so like.
Everyone had a B.
Yeah, like I got 24 out of 60.
Yeah, I got a 21 out of
That
60.
sounds like your normal grade.
Friday.
But that's not what I got at all.
No.
The exam, the like key was messed up.
The key was so messed up that everyone who had an exam B literally got low 20s. I got a 21 out of 60.
And you.
But after
Next.
that, we think 53 out of 60.
I don't know anything.
But
Yeah, just wait for the final.
Bro,
when you
You should, you,
20 out of 60?
huh?
You want us to get a 20 out of 60?
I'll give you a 20 out of 60.
On what?
on the final for this class.
Yeah.
Just meet someone that's just so.
We're just gonna have fun. I'm feeling a little sadistic at the end of the semester.
love this one.
she decided to drop a lowest exam.
Because your room
I told you, there is a bell curve you have to fit.
If I don't show up, guys.
What a pity.
Aren't you on like?
Grades
like-
combined.
You're on like number 512 of your 13th reason.
Yeah, no. I think she might actually be past that. She
So-
might be in the thousands.
This past 512.
Everard, don't make me hate your class.
Too far.
I love your class.
Make me not want to show up next
Double
semester.
checking, because this is happening in a different class of mine. We are not having an exam this week. Exam 4 is the final exam. Okay.
You have a quiz this Thursday. Your last quiz.
Are we gonna be, do we have to show up for the quiz or can we do it
You can
online?
do it on your own.
Okay, so we don't have to be in lab.
It's lab cleanup day, but there's really nothing to clean up. You don't have to, no.
And our final is
But I wasn't.
is gonna be 60 points, not 30.
Now you have to
Yes.
No, not.
Grab the floor. Trevor,
with a toothbrush.
I'm gonna, our final's gonna be 60 points, not 30 points.
What?
I'm old.
How many points is the final?
30,
Well, 30 still?
yeah.
Okay. Over which chapter?
So
In the present.
sound wave comes out, it messes with the molecules in the air, that's a compression wave. That compression wave hits your eardrum acts like a piezoelectric crystal, which does what? Vibrates the eardrum, which produces what that goes to your brain?
Sound signal.
Waves,
The sound is a wave. What does it do to the eardrum?
vibrations.
Right, vibrates the eardrum. That causes a what to go to the brain?
Nerve signal.
I didn't get any of that.
A nerve signal.
Okay, a nerve signal, which is what kind of energy?
Electric.
Electric, piezoelectric crystal.
They're speaking my kind of language now.
Crystals.
Yeah, there are crystals that if you vibrate them, they'll produce electricity. And if you hit them with electricity, they will produce vibrations. Actually, a lot of headphones have piezoelectric crystals in them because the electricity hits them, they vibrate, produce a sound. We found it very, very clear. Not just a magnetic range. I've seen them before. I used to know the company. They're like the high-end stuff.
Thank you.
You have a million.
Like you
those
stink.
like a-
No sane person can.
What's your piezoelectric speakers? So
That too.
you notice here, if you think about this as well, since you guys are having trouble with this, those waves, are those sine waves or cosine waves?
Oh, it's for the way of what? Like a nine. Wait, does it matter?
It does.
They're waves.
Waves.
It's sine waves, because there's zero in the equation.
I forgot. When did we learn about this stuff?
Probably
Hopefully high school.
Yeah, I forgot about that stuff. The waves, how the graphs go.
Now, you're gonna notice the peaks of the waves are at the compressions. Troughs of the waves are at the rarefactions. Nice vocabulary words. Now, we all know that sound dies out over a distance. Find the word up there that describes sound dying out.
Attenuation.
Attenuation. So there's a couple of ways that attenuation happens. You see a geometric attenuation. So your sound wave, your mechanical wave only puts out so much energy. If that's same amount of energy spreads out over a larger and larger area, the sound eventually dies until the energy can't vibrate molecules anymore. Okay, well, what I didn't put it on here, but because I want to see if your guys' logical capacities are working. I fully expect to be let down. So
Yeah. I'll say it.
I love that. No confidence in us.
You just make me feel so good about myself.
Did you? I put mine in warm water.
well, I wouldn't do it if you guys didn't laugh and secretly enjoy it. So see you like that. You guys hadn't started freshman year with sarcasm, we wouldn't be here now.
We didn't start it with our.
Yeah. What's another way attenuation can happen?
I'm being quiet.
Well, yeah, but I call that active prevention.
It hits something that absorbs it.
Ooh, absorption, yes. Attenuation can occur by absorption.
Modulation.
Integration.
You look messy.
You already have the answer and you're still guessing. So,
You change the shape of the medium it's passing.
I do write it.
yeah, so you,
Writing it.
yeah, so. But now, here's something that is a little more advanced than what was in the textbook.
I feel like my number.
Can anyone think of another way attenuation can happen? Imagine two waves meeting each other,
When they hate each other.
destructive interference.
Sounds good.
What's two ways sounds can get louder if waves meet each other?
Constructive.
Constructive interference. She knows about waves.
I know about waves.
Besides, her dad would be super disappointed if she didn't know that.
I would be over this.
Okay,
Is it cute?
the speed of sound waves.
Very cute.
Okay, so the first wave we're going to talk about is a wave in an elastic medium. Kind of think of it like a guitar string. So the guitar string doesn't actually make a sound, it's vibration, puts mechanical energy out into the air, which then causes the compression of molecules, and that's the sound you hear. And it depends on how the compression wave is made that dictates the sound that you hear. So you notice that the speed of a wave through a string is going to be the tension force in the string over mu.
Like that with you.
What do we think? What do we think mu is?
You know, yeah,
Micro.
It's an average.
But it like makes it up. It labels something and it's not micro.
If we were looking at a liquid, what would rho be?
Or
Density.
What is bro? What's on for?
I've just stopped. I'm just like, I'm not even gonna answer. Your answer for everything is cat.
What's row? Let's
Did mu. So
Rho is density, so mu is linear mass density of the material.
row look like though? The V.
I'm sorry, drifting out of the.
Mu is your linear mass density in mass per unit length.
In what?
what?
In what?
Mu is linear mass density, and it's mass per unit length.
You know that makes your hair fall out.
So look here. You have a length of your string, your mass density.
Oh, I see this. Oh, I see.
So the mass of that little cylinder, you have the mass density and then the length of the cylinder.
So the change in M divided by the change in F.
Yep, so let's start thinking about this. Let's go down to you say you have your string vibrating in a wave, like you do down at the bottom. Okay, the first thing you can notice.
No, I don't have hair fall. I have those cookies.
Okay, so we can find the tangent at each one of those locations. Now, we've said it several times this semester. What is the tangent? What is the tangent to a curve?
The rate of change.
So it's a rate of change. We've modeled it as at a single point. So first off, at a single point, if you have a curve, the tangent at that single point is what kind of line is it? It's a straight line that touches the curve at that single point.
Okay, yeah.
So we can find that by looking at the slope of the.
Like my lifeguard shirt.
You have learned nothing in your college career.
True. You're right.
Now, how have we been modeling that slope?
Does that say off or what does it say? The F what? Under tan.
Oh, F sub T, that's the tension
Oh, it's a
force.
T. It looks like off.
What? I'm not seeing where you're seeing off at.
OP. I saw OP. I don't know. It's like it's because I don't know.
Oh, wait.
We can start that
This
way.
part.
Well, we need to figure out where this velocity comes from. How have we been modeling this? Derivative. So that's what we're going to end up working with. Okay, so we take theta 1.
I already have my sugar. Shouldn't I get bought? Yeah. Eat all that.
Yeah.
What?
I'm gonna buy mine probably.
You're gonna replace those tangents with their derivatives.
How about in-
So of course, in this,
But you know what's wrong with those ones? Oh, don't you ever have to sing that? It better not be my karaoke machine. $20.
and then over here, we're gonna get two.
You are what you. That's a funny beat.
Nope, not touching that one. Nope.
No.
Oh.
That's kind of like with the holiday season coming up. If you have a significant other that comes to you and says, I'd really like some of that exercise equipment for Christmas, don't buy it. That is a trap. You get it at a later time. That is a minefield. You don't step into it. Nope.
Brandon got me lifting stuff last year.
And what was your response?
Thank you.
Oh,
She
good.
liked it.
So the people in my
It's a
family have
pink-
found if you buy them something that
Me
they
and Jana
asked
used it.
for, but for Christmas, then it's not appreciated. My grandma wanted a vacuum. My grandpa bought her a vacuum for Christmas and she nearly. blew it.
You do not buy cooking equipment, cleaning equipment, or exercise
The
equipment.
other one was a dishwasher.
Those are minefields. You don't do it.
I asked her.
Because if you do that, the next thing you're going to be buying is diamonds.
Am I stupid or where did hospitals?
Yeah, Brandon.
Stay yes. Which I never understood why diamonds are so precious. They're just hunks of coal that have been compressed. That was actually an ad campaign by the De Beers Corporation in
Exactly.
the 19th century,
They're not even that good. They're.
where they had just piles of diamonds sitting around because they used to not be worth anything. It's like people go out to expensive restaurants now, they're like, what did you get? Oh, I got the orange roughy. It's like, you know what the orange roughy used to be called? It used to be called the slime head, and they found out it didn't sell. So they changed the name of it, and now it's like gourmet.
The slime.
You know, I personally like the slime
I
one.
just eat
Yeah.
chicken.
I wouldn't eat it though.
Oh, really?
So,
Where does that tea go in the first one?
oh,
Special.
there, it was implied. Okay, so. This is just going to be a short foray into wave mechanics to kind of give you an idea where this stuff comes from, and then we'll move on. Okay, so we have that, and then because of Newton's second law,
Basically. Actually, we found it, we tracked it down. Big dude.
and we go back up to the top here where you see that delta M is your mu delta X. And we're also going to take into account, this is the first time you've seen this.
This is on Wednesday and they scared me. I was like, this is me, I'm stopping.
Yep. So acceleration in actual physics is the second temporal derivative of your position. And of course, in a string, the wave is, okay, vocabulary word, in a string, the wave is a transverse wave, which means what? You have longitudinal waves and transverse waves.
It's like, it moves back.
So
Versus a horizontal plane.
that's your longitudinal wave. Look here, look at the sound wave in the particles, that's longitudinal. You see that expanding and contracting. Yeah, transverse wave is, so when your string vibrates, it goes like this. That's your transverse wave.
Okay.
So we're using the derivative of y with respect to time. Okay, so we're going to divide both sides by ft delta x. We're going to take the limit. So inside here, as soon as you have the delta of your derivative with respect to x, so you notice that left side, if we divide by ft delta x, ft goes away, we get delta x on the bottom. And then on the right side, and that limit essentially makes this.
And we're on foot.
So what's going to happen to the left side?
It's gonna cancel.
Nope, not cancel out. Literally just multiply it in. What happens?
Get a second.
You do.
Okay.
Mhm.
It's just a whole bunch of derivations to show signs.
We're talking about waves. You have to see, at least see a little bit of wave mechanics to know where this stuff comes from.
So it's just showing me where it comes from. though,
Yes.
right? Okay.
There are some people in here who want to know it, and there's a lot of people who don't. And people who want to know it will do great things, and other people will just draw blood for the rest of their life. I'm kidding.
You know what? I'd be happy doing that. I would be happy. Come see me anytime.
We got to do a little bit of wave mechanics to kind of understand how waves shape up. So, what we're going to do is now we're going to compare this to the standard linear wave equation. That's a v, so that's the velocity of the wave.
Hey, show yourself. Show yourself.
This is your standard wave equation. This is the beginning of what ends up becoming the Schrodinger equation for high energy waves. Okay, so what we're going to do, I'm going to take this, plug in that. But now we're going to do something that, well, let's see, that's not what's this. And now we're going to do something that drives mathematicians nuts, yet for some reason it gives you the proper theorem. Essentially, those two equal each other, not because we've canceled out the derivatives, but because both,
say so.
it's the exact same second derivative has both of these as a coefficient. So both of these coefficients have to equal each other. And then what you end up with after you move things around is the velocity of your wave going to be the square root of the tension force in the elastic medium divided by the mass density. So this is a very little bit of wave mechanics. Anybody who wants to do a special study in quantum mechanics, we could do this for a whole year.
I'll get to it.
I don't see any takers.
I know nobody actually wants to seems to want to know how the universe works, but
I
Verbally
care
not.
less.
I mean, I can't control anything.
I know, like.
fine. And I guess on the final exam, we're going to have a question about why, when the blood vessel is smaller and you have less depth to the blood in the vessel, that you should have less pressure, but you end up with more.
Be prepared to receive a question mark.
So
Don't worry, I'd write you something.
fluid has to do with depth. But if you have less depth, there's less pressure, yet the body reports a higher pressure.
If you just repeat that question, I could pull up my chat GPT real quick.
That's gonna go bad for you. It's gonna go real bad for you.
You don't think you'd tell me?
Marty.
Why, when the blood vessel is smaller, is the pressure actually greater?
Physics edition.
Because you're using the same amount of flow through a smaller.
Has to do, it's related to the velocity of the fluid,
Is smaller.
not the depth of the fluid. Now, let's talk about the velocity of sound in a fluid. So this one, giving you kind of an idea on the left here of how this is a thing all fluids have called the bulk modulus.
The resistance to blood flow is greatly increased. What's that mean? Velocity.
The blood into a smaller space.
It's like covering a garden hose with some of your thumb.
Okay, so, yeah, there's that.
Inversely proportional to the radius of the blood.
Thank you.
Fish,
So let's
right?
let's also think about which one would cause higher pressure in a vessel, water or oil?
Wait, say that one more time.
Oil.
What would cause higher pressure in a vessel, water or oil?
Which is denser.
This is turning into a
And so you get a higher watt.
For sure.
Lot.
What? Not
What?
what property of the fluid is going to change?
velocity.
Viscosity.
Yeah, that's what I'm.
So you
You
get
just said it
people
wrong.
with crap tons of lipids in their system,
Continue.
you get a higher blood pressure.
Because your velocity. High blood pressure. It's crazy how that works.
Velocity is going to change, viscosity is going to change.
Viscosity, does that mean your viscosity is slower?
Yes.
Please promise me you will study before you take the MCAT, because you haven't done it yet.
I only studied for my test for a month and I did just fine.
Yeah.
I studied for a month,
So that's the velocity, that's the velocity of sound across an elastic medium. Now let's look at this velocity of sound in a fluid. The square root of your bulk modulus divided by what?
See, I thought it was just like density.
Density of the
Yeah,
fluid.
that makes sense. That's why I said good.
So bulk modulus, over here, as you can see, you have, it's, the bulk modulus allows you to compare changes in volume in a fluid to change in pressure, okay? So for each fluid, it's a constant. You can look up bulk modulus. The fun thing is it's usually in terms of gigapascals.
She just. Oh. Oh my God, is this? Yeah.
So bulk modulus is usually in terms of GPA, which tends to be pretty low for most physics students.
I was like, I know how we can. I got it. Don't they have to move their time or like make?
Okay, so
But not like.
well, what about the speed of sound through air? Through air, it's temperature dependent.
Because that's what they did.
Does
So-
it travel better in cold or not?
You know, and so keep in mind, this top number in each one of these velocities is a restorative force. Okay? In the material, it was tension. Your bulk modulus has to do with restorative force in a fluid to its original volume. Now, we know that bulk modulus, for example, if we think of gas like a really thin fluid, it's proportional to the density times the temperature. And so if we say that the velocity
There's like all the optic stuff, not like the optic.
and we replace that, so velocity is then going to be proportional to we find out that velocity ends up being proportional to the square root of the temperature of the air. And so you end up with this equation here where your sub-zero, that's going to be a reference speed and temperature. You're going to have charts with speed of sound in air like 0 Celsius. Your zero is going to, so your T is the temperature you're at. T0 is a reference temperature. Your V0 is a reference velocity at T0.
So you'll like find those.
And then for a non-elastic solid, speed of sound in a solid, again, is going to be the square root of your Young's modulus divided by the density of the solid.
So the like a string and this one's like a wall.
Yeah, so the first one was elastic. It could be deformed. This would be like a block of steel. I guess technically a block of steel can be deformed, but for all senses and purposes, like if you were punching a block of steel, guess what's not going to happen? You're not going to deform the block of steel, it's going to deform you. So,
Shit.
and again, your Young's modulus is something that's going to be unique to a material. You can look that up. Like for example, your Young's modulus of an amino acid molecular crystal is 21 to 44 gigapascals.
How much pressure you have to apply to the orbit?
Well, so more than anything, what you're thinking about inside of a non-deformable material is the sound's going to go through and it's going to vibrate the molecules in there a little bit. But inside that solid, those molecules are usually very fixed inside a crystal structure.
Okay.
The Young's modulus is going to be a measure of the restorative force to the crystal that's no longer moving.
Okay.
It's going to be pretty much the pressure, a measure of internal pressure created by the mechanical wave passing through it.
So it's like resistance.
Pretty much, yes. Okay, so let's see if we can solve a problem. Dolphins emit ultrasonic waves. The frequency is high as 2.5 times 10 to the 5th hertz. First off, what is hertz in SI units? So it's frequency. What is hertz in SI units?
Hi.
And what is the SI unit for hertz?
Frequency?
Hertz is a measure of frequency. What's the SI unit? There's something with a -1. No.
The letter?
You say it's a letter?
Second, was that negative?
Inverse seconds.
I said S, did I not say S at the beginning?
Just say it louder.
Be glad I'm talking.
How many times do I have to explain to you guys? My ears are not only 43 years old, but I used to do security for rock concerts, okay? You have to speak audibly at a reasonable volume. No. So hertz. Inverse seconds. I'm surprised nobody got this one.
Said to the man,
Yes.
stand. I was singing the song over here.
Were you-
I just said, Gani, wait.
Do you know there are 7 of those videos?
Yes, I've seen every single one.
I just found out that there's 7 of those. Kind of like the llamas and hats.
Oh my God, llamas hats. No, marshmallow people.
I haven't seen that one.
Or have you seen Charlie the Unicorn?
Yes.
Where they just try to kill
Candy
him?
Mountain, yes.
You see the Let's Go Hunt a
Charlie.
Have you seen the chaotic good barbarian?
Is that the one that's like, we're going on a bear hunt?
Oh,
that
one.
Yes, I did.
Life with Brian movie.
I told you if you're easily offended, don't watch it.
I wasn't offended.
Apparently she was.
No, I wasn't. I said there was full frontal nudity. I was not. No, yeah.
First off, for like 2 seconds. Second off, I'm gonna refer you back to the Patrick Swayze marathon y'all had. And did we talk about some of the scenes in those movies?
Yeah, I didn't watch those. Let's just say I had to pay attention a lot to follow what was going on.
I'm just gonna come in and start playing the song Always Look on the Bright Side of Life and what. Okay, so
Brian. Yeah, poor Brian. It's Brian.
what is the wavelength of the sound wave in seawater at 25 Celsius?
It's just
Bulk modulus of seawater is 2.34 gigapascals. And the density of seawater is 1,025 kilograms per cubic meter. Okay, so how do we find wavelength? How do we relate wavelength? So we have all these equations we can solve for the speed of the wave. How do we relate that to wavelength?
What?
You're looking for the Greek letter nu.
Yeah, it's the compression to the compression.
So let's think of this. The velocity of a wave is nu times lambda. What is the Greek letter nu? It's frequency. So if we have the wavelength by doing 1 over nu square root of bulk modulus over density. Okay. Okay, so that's going to be, so what the frequency. Okay, so 2.34 gigapascals. What is the suffix times 10 to the what for giga? Not 6. 9. You were.
She said it upside down.
I was 6 and I get it. Never mind. I get it. And the Pascal is the Newton per square meter. So your lambda, when you come out to be 6.04 to the negative third meters, or 6.04 millimeters. Sound waves are much, much longer than light waves. Okay, so using that kind of idea, We have a few minutes. I want you guys to start working on this one. I will actually go through it, so I'll tell you for A. Those are the answers you're looking for.
Is it? Like if you were to draw a head.
Yeah, so you have to use that
It's not.
because
Not what my.
you notice you have a reference speed and temperature.
How do we find what it is?
I see the verses.
Yes.
Well, you're gonna want to change everything to Kelvin first off.
See the head.
So you remember the temperature dependence of velocity, we had the equation for the temperature dependence of velocity in air.
Yeah, but velocity equals the
V zero is
V0
your reference
in
velocity,
your square root.
your new temperature, which is 12 degrees Celsius in Kelvin, over
Okay,
your
yeah,
reference temperature.
I was reading that all wrong.
That, in the case of that equation, the sub-zero is a reference speed and temperature. Something you can usually look up. RNA transcriptase.
Trauma. Do you know about RNA transcriptase?
Honestly, I'm not real sure. That's not my area.
Well, that's what I'm saying. It's direct. Look. Biology and that.
I did. It did not go well.
Never played any in our. You just have to take like a,
For me.
did you just have to take like an intro to like our.
I did, but I also, since I was a double major in physics and chemistry, I also had to take biochem, and it was just not.
Oh,
Because
don't get me started.
my professor had those like little space filling plastic molecules. She would go, "Do you see the beta term there?" I was like, "No."
You see how this, no.
She's like, "Well, what do you see here?" I'm like, "Big goop."
And she was like,
I see a reason.
physics majors.
Yes, you pretty much, yes. That's how I ended up getting bad grade on my final exam in physical chemistry. Because the professor put on there a heat engine and said, solve this heat engine and explain based on your numbers why it works. I solved it and said, for all sense and purposes, it doesn't work. And he goes, no, I'm going to give you a chance to redo it. When I was young, I couldn't control my intrusive thoughts. So
You said, no, it doesn't.
I can quite a bit now. But so I said, no, it doesn't work. And he goes, well, why don't you explain it to the class, physics major? Why don't you explain to all of us chemists why this doesn't work? And I go, okay, that was my mistake. Because I showed the math on the board and I said, the engine you put on the exam is 3% more efficient than a Carnot cycle. So unless we all have 2 lifetimes of the universe to wait, it doesn't work. So the proper answer was, I apologize and I should have left the room. That's not what I said.
Yeah, it said you showed him.
Yes, and then he gave me a D on the exam.
That's what got her.
Okay, so we'll finish solving this next time. How close did you get?
I mean, it's